Welcome back to my material science class. As promised in the second and third parts of this introductory series to properties of materials, in this video I have a comprehensive set of calculations on strain, elongation and elongation percent. In this video I'll show you 6 sample calculations where calculation 1 will be the easiest, gradually progressing in difficulty to calculation 6. I'm trying to take not much more than 20 minutes up with this, but it also needs a little explanation. That explanation is going to be on transposing or working with equations. I'm not going to explain any of the terminology and any of the symbols. All of that information was discussed in great length in video 3 or part 3 of this series. So the equations that will be referred to are these. The red one for elongation or deformation. The green and the blue stuff is essentially the same. Both of them are strain calculations or strain basic equations. These basic equations have some variants to them because this one here for elongation has 3 terms. There is 2 more equations. Just going to change color. 2 other possible equations can be made out of this one, so that's a total of 3. The same with this thing here in green. 2 more equations are possible to be made to calculate strain, so that's a total of 3. And on this blue stuff there's one more variant on it that can be made mathematically, or that can be made out of it. So we have a total of 3, 6, 7, 8 equations. So in the following 6 sample calculations I'll use 5 or 6 of these possible 8 equations. This is how the equations look like. Now, if you don't have to memorize all this. Let me show you a trick here. You only have to memorize 1 for elongation and 1 for strain. That's it. And especially these ones are the easiest ones because these reflect material's journey from no load to fail. Because this one has final length and initial length given in them. These 2 versions are easiest to memorize. So how can you recreate the rest of them if you don't have a math background and you don't know how to transpose equations? Fairly simple. Just follow this little song and dance here. What you do first is replace those letters with numbers. Pick some easy numbers. I'm going to use the numbers that were featured in the third part of this series of videos. So the final length of an eraser chunk was 120 mils. This was 100 and this was 20. So that's step 1. Step 2, write up what you want to calculate. So in this one, delta L was calculated. And you need 2 more equations. You need 1 equation, you don't have that stuff available, and you don't have that stuff available. You write down this because you need to calculate, besides the third term, elongation, you need 1 version that calculates final length and 1 version that calculates initial length. So all you write down is LF equals, LI equals. Oh, math reads back left and right to left. Don't worry about it. If I write it backwards, don't worry about it. It's math. So that's step 2. Step 3. LF was 120, so you write down 120 there, and LI was 100, so you write down 100 there. 120 equals and 100 equals. Step 4. Using only the numbers 120, 100 and 20. How can you combine the numbers, the remaining numbers? You only have 100 and 20 to choose from. The remaining 2 numbers, how can you combine them that they equal 120 in a single step operation? Fairly straightforward. The 20 needs to be added to the 100. Or the other way around. Its addition is commutative, so either which way is good. So it's fairly straightforward. So that's step 4. Step 5, replace your numbers with letters. So 20 was delta L, so you write down delta L, and 100 was length initial, so you write down length initial. Done. Same thing repeats here. How do the numbers combine that they equal 100? And you have number 120 and number 20. Fairly straightforward. 120 minus 20 will equal 100. And again, once you have the numbers, you replace the numbers with letters, just like so. How about that for algebra? So this procedure here replaces algebra and transposing equations. What do you think? Same applies to this one, just a little bit different. The Li and the epsilon can trade places. That's a step that you memorize. So how the second equation comes about is almost the same. It's still a division. Just these two terms are traded places. The third equation comes about if these two guys are multiplied and they equal the remaining third term, delta L. So that's what you see here. They are multiplied. Now, to check it, just to make sure that they are all right, delta L was 20, length initial was 100. If you divide 20 by 100 and press the equal button on your calculator, you better be seeing 0.2 there. So that's your third term. Check this one, make sure it was written up correctly. Enter 20 in your calculator, divided by 0.2, press the equals button. You better be seeing 100 on your calculator's display. Do the same with the third one. That's how these equations came about. Okay, so this is a little trick. We'll call it a trick that you can do with terms of a division. You know, you can flip terms of a division like this way. This equation here in blue is essentially the same as this, just delta L has been replaced with this equation there, so that's, I'm not spending any story on that one or any time on that. And this one came about with a combination of reshuffling letters and replacing letters with numbers and whatever. So how do these numbers equal to 120? That's how. Okay. So that's just a trick if you don't know what to do with transposing equations. Let's get started with, I'm just switching this one over. Let's get started with the calculations. So this is how the calculation sheet looks like. I've got a little bit of a coding on it going on. The given information in every calculation is underlined, so those are the given numbers. That's all you have to start a calculation, consistently marked on this sheet. And the requested information that needs to be calculated is bolded everywhere consistently, so that's what you need to calculate. That one, that one, that one. Okay, it's bolded, so that's how this looks like. On your subsequent worksheets and quizzes, this clue is not going to be there in the text. So you're going to have to decide for yourself what is given information that you can use for calculation and what is requested information, what needs to be calculated. Now, let's get started. So the first question is the easiest because of two reasons. One, it reflects material's journey in a chronological order. So we have length initial given and length final given. So that's the way materials fail. And the three quantities are quite explicit that need to be calculated. Elongation is specified, elongation percent is there specified, and strain is also specified. So fairly straightforward. Now, they are not listed in the order that they need to be calculated, so that's a little bit of thinking there to do. That's up to you to do the thinking. First thing you need to calculate is elongation. Second thing you need is strain, and from strain you can calculate elongation percent. So that's going to be the order, but again, so that's for you to decipher or to decide. Alright, first things first, elongation or deformation, fairly straightforward. You can write up your formula if you want, figure out a system how you want to work these word problems. If you want, write up the equations. That delta L equals final length minus initial, and then on the next line delta L equals 2.65 minus 2.5, and then the third line just write delta L equals 0.15. And now look at this one here, it says inches, so make sure your unit of measure there is inches, and it's clearly and plainly visible. Inches. I don't need inches repeated at every number, but I need the final answer with the correct unit of measure. Okay, so that's how this looks like. Figure out a system that works for you. Next one is strain. Strain is calculated by dividing elongation with the length initial, or you can just go 0.15 divided by 2.5, which equals, here is calculator, 0.15 times 2.5 divided by 2.5, 0.06. There. So that's strain, and from strain, if you multiply strain by 100, you're gonna get elongation percent. Like I said, this is math. I write it left to right and right to left to get used to it. So elongation percent equals just 6%, just put it down there, that's it. Strain and elongation percent don't have a unit of measure. They're just 0.06 or 6%, done. There's no need, there's no unit of measure there. So that's the first one, simplest one, easiest one. Moving on to the next one. Oh, I forgot to mention, this one says steel. Yeah, don't worry about it. These numbers, this 6% elongation is actually characteristic of steel, but it could be, like I said, the chunk of eraser. Any material can be considered. So the next one also reads steel, don't worry about it. The next after that just says metal, and then just says a bar, and then it says metal wire, and then it just says material. Don't worry about it. No, that is not important. We're just doing the math here, okay? So, next one. Calculate the elongation of steel if you have length initial, length final. So this is harder, but it still features materials journey in a chronological sequence. You have length initial and length final, but you only have elongation requested. But it also says at the end of the sentence here that express your answer as a percentage. Now, what makes it more difficult than the previous one is that the requested information is less explicit. Elongation is there mentioned, elongation percent is here mentioned, but you can only calculate elongation percent here through calculating strain. So strain is nowhere near listed in this, but you have to calculate it before you can calculate this. Alright, and also this one doesn't say elongation percent, it just says as a percent. So that's also a layer of implicitness in the word problem. So fairly straightforward. I'm going to choose a different layout for this problem. You can just write 57 minus 50, and you can just go with delta L equals 7 millimeters. It's millimeters because that's the unit of measure there. Done with elongation. Next one, you need strain. You can write for strain 7 over 50. Strain is done. I don't care if it's a fraction, as long as it's correct. It doesn't have to be fraction in the lowest terms. You can also write it's 14 over 100. I know it's kind of microscopic. I kind of worked myself into the corner there. Whether it's 7 over 50 or 14 over 100, it's the same fraction. It's not the same fraction. It's both of them are fractions of equal worth, and they are both correct. I don't care. You can write it in a decimal if you want. In decimal it's 0.14, because 14 over 100 is 0.14. So that's either one of these numbers is good enough for strain. And for elongation percent, I don't need to see the equation and how you calculate it. You can just do it like so. 14% equals the elongation percent. There, I kind of need to know what the hell 14% is, so make sure you do mark your sheet clearly enough however you lay out your numbers. So this one is somewhat of a messier layout than the first one. Just figure out a nice and neat system for yourself, okay? And make sure others understand it. Now next one is more complicated a little bit. By how much did the metal get longer? Now, in the sentence, get longer, let me just slide it there. Get longer implies the word elongation or deformation. Okay, it doesn't say that word for word, like calculate elongation. It just says get longer, but get longer means elongation. Now, you don't have a final length here. You have an initial length, and then you have an elongation percent. So, you need another equation other than materials journey in a chronological order. So, let's look at this one. What we need to calculate is that one, delta L, and we've got length initial, and then what else do we need? We need strain. Do we have strain? We don't have strain. We have elongation percent. So you need to calculate strain out of this. And that's also just implicitly contained in the information. So fairly straightforward. This 21% needs to be divided by 100, or you can shift the decimal to 2 spots like this and just write down strain is 0.21. I don't necessarily need to see an equation that, but the equation would look like elongation percent divided by 100 equals strain. That would be the equation, and then 21 divided by 100 equals epsilon, and then the last line 0.21 equals epsilon. Something like that, but this also works. So now we can calculate delta L by multiplying length initial with epsilon. So that's 5 times 0.21, and that's going to be a little over 1. There, that number, 1.05. So just write down delta L equals 1.05. Final answer, need a unit of measurement, meters. Done and done. Okay, so this was harder because it's not chronological, and it has some explicit information, stuff that needs to be inferred there and there. Next one is harder yet again. Let's see, that's good, you can read that one, almost there. What was the initial length of a bar if its elongation was 10% and it got 5 centimeters longer? Again, it's got longer in it, so that means elongation there, and elongation percent is just elongation percent. Alright, so it's basically the same as the previous calculation was. Delta, it has some, in terms of that, it has a bunch of inferences in it. In this one, initial length needs to be calculated. Let's go back up to the equations. How is initial length calculated? That's how. Delta L needs to be divided by epsilon. So let's go back down here. Delta L over epsilon. Alright, do we have epsilon? No, we have to make epsilon again out of elongation. Fairly straightforward from here on. Delta L, so that's just 5 centimeters. So 5 needs to be divided by epsilon. Alright, the 10% again, I'm just going to shift the decimal place to 2 places to the left. Strain is 0.1. So once you have 0.1 here, you can just enter it in your calculator. Not 0.5, just 5 divided by 0.1 equals 50. There. So initial length is 50. Let's see, 50 what? Oh, centimeters. There, this is your final answer. Now, what kind of a machine is it that needs a 50 centimeter sample, or in the previous one, a 1.05 meter long sample? Don't worry about it. We're not going to the lab with this stuff just yet. We're just doing math, okay? So most samples are normally seriously like 2 inches long, so 50 millimeters long. So just don't worry about these strange or odd units of measure. This is just math only. Okay, lab is going to be lab with realistic units of measure. but the numbers are by and large realistic. Most steels have a 10% elongation, etc. No, they don't really stretch 5 centimeters. They do stretch 5 centimeters if they are 50 centimeters long in the first place, but yeah, so for lab you'll get realistic units of measure. Next one is even more difficult than the previous one. The reason for it, because it's going to need two equations ultimately. So it gets longer again, that's implied, that's delta L. Final length is final length, strain is strain. So those are all the requested information, and what's given is length initial and elongation percent. Now, you don't know which one to calculate first, so that's why it's more complicated. And length final, none of these equations up here contain a letter length final, because there are 8 equations like I said, but I only wrote 3 of them up there, and for the final length you need a second equation. That's why it's harder than any of the previous ones. So in this case, strain can be calculated from elongation percent as per standard procedure, divide by 100, or I'm just going to shift the decimal 2 places to the left, so I'm just going to write down 0.142, sorry, doesn't need a dot, the 0.142, there, done, that's strain. So strain is being calculated. Next thing to calculate, how much the wire gets longer, and that's fairly easy. Once we have strain, we need this equation yet again, where strain and initial length are multiplied. So let's do that. Initial length was 4.2, so it's delta L will equals 4.2 times 0.142. So 4.2 times 0.142 equals that number, 5964 after the decimal dot. So that's delta L, and its unit of measure is centimeters here, so put down centimeters there. So that's elongation. So out of the 3 requested pieces of information, 2 are calculated. Next one, final length. Alright, for final length, very straightforward, you need to add, because length final equals length initial plus elongation. That equation isn't up there on the top of the sheet, that's in your memory bank, eventually it's gonna be there. So what you need to do is add to this number here 4.2. When you do so, you will end up with, still on the calculator's display, plus 4.2 equals that number, 4.7964. At this point I want to point out that I used the second blue equation, which was shown or on the board previously, but instead of using one blue equation, I chopped it into 2 parts. This would be one part, and the other part would be, when we did this calculation here, length initial times epsilon, and to it we need to add length initial again. So that's how the second blue equation looked like when it was on the board. Last one is the hardest of them all, very similar to the previous one. It says calculate the final length, and that's the only requested information with no other clues what else needs to be calculated. But again, because it's similar to the previous one, it's going to have by and large the same flow. It has length initial given and elongation percent given. So what you need to calculate is epsilon. You need to calculate out of length initial and epsilon delta L, and then you have to add length initial to delta L to get final length again. So it's harder because again it's still not chronological, and it's and how final length is calculated is only implied, that you have to calculate strain first, and from strain delta L. or not from strain, but using strain, you need delta L. So it is 0.032 because I'm just shifting the decimal dot 2 places there and filling it in with zeros. So that's the strain calculation. Make sure you have the correct number of zeros everywhere, alright? It does not have a unit of measure. Delta L will be length initial times strain. Length initial was 2, so I'm just going to double this number at 0.064. It's done. You can multiply this kind of stuff in your head. I don't need to see calculations necessarily, that's why. Inches or a quotation mark or whatever, mark it as inches. So that's done. And to this you need to add 2 to calculate final length, and you can just, because it can be done in your head, you can just write down 2.064 inches for final length. There, that's basically all there is to it. On some of your worksheets you'll get an answer key that looks like this, where you have everything listed, and yeah, on some of your worksheets. Some other stuff we'll check in class. So what you can do, besides checking your answers to make sure you're on the right track, is for further practice, change the numbers. Change just one of the numbers. Instead of 2 inches, recalculate it with 3 inches. I don't know. So you can practice the calculations and generate your own practice problems a little bit. So just change one number or change 2 numbers. Eventually you'll realize that out of the 8 equations I only used, I don't know, maybe 5. So you can generate practice problems for yourselves with requested information that none of my practice problems show. Okay, just come up with new practice problems for yourselves. So that's basically how these calculations go. Again, how practical it is in lab that you only have initial length and already have the final elongation percent calculated, and you need to know the final length. Don't worry about it. This is not lab. Okay, this is just the math to reinforce the math and get your head working around the concepts of what's the meaning of initial length, what's the meaning of final length. How do strain and elongation percent relate to each other? How do all of these terms relate to materials journey? That's the point, okay? Not whether there are meter-long pieces in the lab or not, okay? So that's besides the point, okay? The point is reinforcing the concepts, the meaning of terms, and how they layer and build up into bigger and bigger concepts for materials journey from no load to failure.